All right. Good afternoon, everyone. Welcome to Intro to Space Navigation, Spring 2025, Lecture 25, and our second to last lecture for the whole course. And as a reminder, we are in our 4-lecture long optical navigation series. So this is image-based navigation and image-based position estimation, right? Because we already had a 4-lecture long series about how star trackers work, which give you your orientation. So lecture 23 and lecture 24 were about horizon-based optical navigation, how to start with an image that looks like this, and then determine your position with respect to this planet, given these horizon points. There's some sort of geometric relationship between these horizon points, the overall shape of the celestial body that you're working with, your orientation, and your position. And that relationship is captured here at the end of lecture 24. So that's everything we need for homework 6. So those of you that are attempting optional homework 7 is on crater-based navigation. So kind of estimating your position and your orientation from craters on the surface of the moon. That is homework 7. That is actually the next lecture. We're kind of going to break sequence here. So the final lecture is going to be homework 7 material. And then today, the second to last, is going to be homework 8 material. And full disclosure, this is an untested lecture. So every other lecture this semester has been an improvement on a corresponding lecture from last semester. So I kind of went over my notes and decided that certain things weren't important to go over and certain things really we needed to linger on more. But this one we're doing live for the first time because this is new material that was not covered last semester. So we're going to see how this goes. So let's see. The question today is, let's see here. I'm going to start with 2 rectangles. And then do another one right next to it. It's about the same size. There we go. And the question I'm asking is, let's say that these are images of the surface of the moon, where you've got like a crater here, and you've got another crater here, and then you've got a third crater down here, and then maybe you've got some smaller features, some other little bits and bobs over here, and then this, and then this. Okay. And this is some image 1 taken at time 1. Image 1. And then at some time 2, and this could just be seconds later, you take image 2. And image 2 looks like this. Crater, 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 little guy, doop, doop, and then maybe big crater, and then these other little guys. Okay. So the question is, what can a spacecraft determine about its state from a set of before and after terrain images? And that is not a rhetorical question. What do we think? What can we do with image 1 and image 2?
Well, I mean, you already kind of know what direction you're going based off of where previous locations now are.
Now how did you do that? Your brain just did something automatically that we're going to need to teach a computer how to do.
Identify patterns.
Yeah, so you saw this triad of craters, and you said this one is this one, and you said that this one is this one, this one, oops, let's pretend that's a straight line, is this one, and you'll notice that also this point is this point, this point is this point, and last one, this point is this point. So what your brain does more or less automatically is it says, okay, here is a set of points in the first image, a corresponding set of points in the second image. And I know that they didn't really move, right? The craters on the surface of the moon are not moving around. What happened is I moved. And so I can determine what direction I'm going. Katie hit the nail on the head with that. You can determine what direction I'm going just based on before and after images. And so the topic of today is going to be twofold. First, we're going to talk about image features, which is something that our brains do automatically, but we need to teach a computer how to do. And if you're determining the direction that you've traveled from information in an image, that is called visual odometry. Like the odometer in your car tells you how far you've gone, right? That kind of idea. We're doing visual odometry. Okay, so we can determine by tracking the apparent motion of features which don't actually move. You can determine at least the direction of spacecraft motion. Distance is actually a bit harder, as we will discuss. As a matter of fact, for a monocular camera, there is, and this is the there exists mathematical symbol, there exists a range ambiguity. Problem with a monocular camera. So if you just have one camera taking before and after images, you're not actually going to get your distance traveled. You're just going to get your direction traveled. So therefore, we can find direction of motion but not distance. At least not with this particular method. Now, if we had a stereo camera pair and we were doing this with a pair of before images, like left eye, right eye, and then a pair of after images, then you could actually determine your distance that you've traveled, provided that you've done some sort of extrinsic calibration and you know the baseline of your cameras, right? But a single camera, no depth perception, there's a range ambiguity problem. Are we zooming over features that are close to us, or are we moving slowly over features that are very far away? How does that work? And so in order to do this, we will need number one, a method of detecting and matching robust image features. And then number two, a method of estimating camera motion from corresponding before and after points. And that is visual odometry. Okay, questions about the general premise of what we're doing today? Okay, so the first thing I want to linger on is the image features part. So I specifically drew a pattern that your eye would be able to recognize in both images, but in order to make that automatic in a computer, it's a little bit more complicated than that, and we use what are called image features. And some of you might actually know a good deal about this already, depending on your background. Image features. Okay. So there are many types of image features. Each developed by a different group and each with unique strengths and weaknesses. Some examples are so the big one people talk about is called SIFT, which we will spend some time on today. So some of you might have heard of SIFT features, but SIFT is not the only game in town. There's also Surf, there is Orb, and there is K's, and there is Brisk, and there's also what are called Harris corners, to name a few. And so in this lecture, we will focus on SIFT, the most well-known, with the understanding that others are good as well. Okay. So the idea behind an image feature, or specifically a SIFT feature, is something about the image, which does not need to be a recognizable thing to a human eye. This is kind of the strength of SIFT features. SIFT features can be information in just a few pixels that is recognizable under different transforms. So you might say, okay, we're going to determine the relationship between image A and image B. We don't need to look for entire craters. It could be individual rim points. It could be individual just fluctuations in the brightness in the planes of some flat region. I mean, an image feature does not need to be something that is physically meaningful, right? Rather, it's something that the computer can detect reliably. These are the the big two things. It needs to be something about the image, and I realize that something is kind of nebulous. We're going to go into that. Something about the image that the computer can detect reliably and that it can put a label to. So now we're back to like the star ID problem, because ultimately we're going to need to say, hey, computer, find the SIFT features in image A, find the SIFT features in image B, and now find the point correspondence between them. Right? And that's a pretty well-trodden path. There are inbuilt MATLAB and Python libraries that will do that for you. So actually, in my opinion, homework 8 is probably easier than homework 7 because a lot of it you can do with inbuilt libraries. But it's still, you know, we'll need to go into the gory details of exactly what's going on under the hood. We'll at least cover it at a high level today. But yes, it is in theory possible if you wanted to kind of code up your own SIFT or even come up with your own image feature. I mean, it's not impossible to come up with these, but I would recommend against it. I would say, why reinvent the wheel? Let's use some of the features that are already out there. So SIFT, by the way, stands for scale invariant feature transform. So you should be able to recognize, or I should say a computer should be able to recognize a SIFT feature, even if it's upside down, even if there are at least some moderate changes to lighting, even if it's smaller, which it's wild. Imagine that you've got, I don't know, a photo of somebody's desk with a deck of cards on the desk. And then you have another photo of somebody's desk, but the deck of cards has moved and it's moved away from the camera. So it's smaller, right? So you're not just doing a template match trying to find the same pixel oriented. Like, no, it's a different object to somebody without object permanence. Which a computer doesn't have object permanence, but a computer will be able to say, oh, this cluster of points in the first image is this cluster of points in the second image, even though it changed size, and even if it maybe rotated a little bit, which is pretty darn impressive. So as I've been yapping about, let's just put this into words here. all image features, not just SIFT, all image features consist of at least 3 capabilities. I guess I boiled it down to 2 earlier. So there's feature detection, by which we mean what in this image is unique. And then there is feature description, which is saying what numerical name tag can I give this point? And then there is feature matching. I guess before I rolled those into one. So description and matching are related, which is really just comparing descriptors, right? So this is the point correlation based on descriptors. Or I guess name tags. So if you have a good name tag, which is robust, then it's trivial to go through and find the correspondence. But finding a good name tag is kind of the tricky part, as is the detection. So I'm going to go through, let's see, a page worth of notes on how SIFT works, with the understanding that this is optional. If you feel like treating SIFT as a black box, you can. I just think it's neat to spend a little bit of time thinking about what's going on under the hood, but this next part, this is optional. You could still do homework 8 if you were not paying attention. Maybe I shouldn't have said that because now I was going to pay attention. But here's a little bit of what's going on under the hood with SIFT. Feature detection specifically. Whoops. So SIFT begins by creating a 3D image stack. That can be searched for extrema. Okay, so we will take the raw image, convolve with a Gaussian kernel, so we basically blur the image. Then subtract the two. So we're looking at, here is an image which we've blurred, and an image which we've blurred more, and then we're subtracting the blurred image from the more blurred image. When you do that, that is called the difference of Gaussians. When you do this, certain parts in the image are going to pop more than others, depending on the scale of the thing in the image and the amount that you blurred the image. Okay, and then you do this for several kernel sizes or blur factors, basically. So a larger kernel means you blur the image more. Do this for several. Actually, you know what? Might have a mistake. I believe it's the same kernel size. I think it's several Gaussian distributions. So basically, you're changing sigma. You're changing how blurred the image is. And then let me just make a note to self here. I have a mistake. Different sigma. Yeah. And the next thing we do is we scan through this difference of Gaussians block to find extrema. So imagine, maybe I'll make use of, imagine we've got an image, and then we have that same image this way. This again here. And we're comparing the image blurred to the image blurred again. And when we do that, we get kind of this difference of Gaussian image. And then we get another difference of Gaussian image. Looks like this. And we ultimately are building a block over here, which we're going to call the dog block. Difference of Gaussian block. And so you can imagine this is basically a three-dimensional shape where the x-axis, you can think of it as here is U, here is V, and then here is sigma, right? A different amount of blurring as you go down the image stack. And you're looking for within this image stack, what pops? What are the extrema? Right? And when you're looking for extrema, you can numerically approximate the gradient and Hessian at each point. To find these extrema. And basically we keep only features with sufficient contrast. And also you test to see if your image point is an edge, right? We want something about the image. We want an extreme point, but we don't want that extreme point to be an edge. Because imagine you've got an image that looks like this, right? And half of the image is black and half of the image is white. And let's say that you determine that, oh, hey, something interesting is happening right here in the image. Maybe I'll do a different color here. You say, oh, something interesting is happening right here in the image. Look, it's going from black to white. You go, okay, that is interesting. There's a sharp gradient there. Okay, great. The problem is it's an edge, which means that it's going to look exactly the same as this point. So edges make terrible features. Corners make better features because in general you have fewer corners. But I just want to get that idea across. We look for points with sufficient contrast and we throw out edges. Okay. So what we have now are points that we can detect in image A, and in theory, we should be able to detect those same points in image B. Now, that doesn't mean there won't be points that we find in image A that we don't see in image B, and there might be points that we find in image B that we don't see in image A. It's going to be like a Venn diagram, right? There's going to be several image A points, several image B points, and we're after the ones in the middle of the Venn diagram, which can be found in both images. And the way we can detect if something is in both images, we need a feature descriptor. So next is SIFT feature descriptors, or let's say description.
Professor,
Fine. Yeah.
what does blur mean in the context of like the sigma direction in the dog block? Like you're saying they're creating a 3D image stack.
Yep.
Of blurs. Like what is?
So the idea is you take an image, you blur the image, and then you subtract the two. Right.
And
so then
the difference in what resolution is the sigma?
The sigma would be the amount that you blur the image. So yeah, so you would be looking at, here is some image which is unblurred, and then here's an image which is blurred, and then here's an image which is really blurred, which I realize I'm not using numbers.
Okay, that makes more sense.
More and more and more, right? And then you look at, okay, so it's a difference between, maybe this is the sigma 2 minus sigma 1, and then this is sigma 3 minus sigma 2, that sort of thing. Does that help a little
Okay.
bit?
Yeah, that makes way more sense. Thank you.
Okay. And all this comes with a caveat that I am not an expert in this field, and I just read the original SIFT paper, and this is what I got out of it. But there are people on YouTube that will do a much better job than me at explaining this stuff. So we're gonna do our best. But I'm kind of learning this stuff too. Okay, I'm gonna drop a rectangle here, which we will need later, and I'm just gonna work around it. Okay, so how do we describe a feature? Let's say we found a point in an image that we think is interesting. How do we describe it? So we start by assigning orientation to the point. To the feature. Okay, so what we're going to do is, let's say that there is a point in the image right here. Okay. What we're going to do is we're going to sample in a region around the image. I guess I'm kind of skipping ahead here, but basically, I'm kind of presupposing that we know the orientation. There's something about this image that has some type of orientation. What we're going to do is compute the magnitude and direction of the image gradient at several points near the feature. And then the next is to say, we form an orientation histogram. So we say, okay, we pick a point near the image, pick a point near the key point. We compute the magnitude and direction of its gradient. Let's say it's pointing this way. And then we also find the magnitude and direction of the gradient over here. Let's say it's pointing this way. And then we find another point over here. Let's say it's pointing this way. And then this point over here is pointing down this way. Right? And we let them all vote. We make a histogram. We say, okay, this many points are pointing at this degree, kind of clocking around the image. So we'll have different bins for different angular resolutions. So we're forming an orientation histogram with 36 bins. So 360 degrees, 36 bins, 10 degrees each. So all of the feature points near the original feature point with an orientation between 0 degrees and 10 degrees, they all fall into one bin, if that makes sense. And this is filled with subpixel sample points. In a windowed region around the feature. Okay, and the highest peak of this histogram, so you basically let them all vote. The highest peak of histogram is our key point orientation. So we let a whole bunch of sample points near the point of interest vote on what the strongest gradient is. And on average, they all said this way. So there's the overall feature orientation. Okay, that is still not a descriptor. Okay? So the next thing we do is we express subpixel gradients as angles with respect to the key point orientation. Okay. Now, because we're working with respect to the key point orientation, this gives us our rotation and variance, which we're so excited about, right? If you can only recognize a deck of cards in an image every time it's perfectly upright, what good is your image feature? It needs to work if the deck of cards is rotated. So we'll say, okay, here is an image feature. On average, the gradient is this direction, but really each point had a different gradient, remember? Now we're going to express each point's different gradient, not as an absolute direction in image coordinates, but with respect to the overall feature direction. We sample a 16 by 16 grid around the key point. And we produce 4x4 orientation histograms with 8 bins each. And these numbers might sound kind of arbitrary, and they are. Image features are definitely more of an art than a science. So let's say around this original point, we're going to start scanning and we'll say that within some windowed region, maybe we end up with something that looks like this. You can clearly see, Mom, can we get a rectangle? It's like, no, we have rectangles at home. This is the rectangles at home. And so we'll say, okay, within this area here, the key point is this way. Within this area here, not the key point, the direction of the gradient is this way. And then maybe we'll say this one is this way, and this one is this way. So we're taking this and then we're combining. So out of the original, it's going to be 16 by 16 grid. Then we produce 4x4 orientation histograms with 8 bins each. And you can imagine building for that 4x4. We basically let them vote. So this one thinks that we've got an orientation that points this way. This one thinks we have an orientation that points this way. So if you combine those, we've got some votes this way, some votes this way, some votes this way, some votes this way. And we would do this for all of the different grid points around the original key point. We take all histogram entries and we put into a vector. So we've got, let's see, there are a total of 16 histograms. They each have 8 bins. So if we're going to keep track of the number of votes in each bin, and there's 8 bins and there's 4x4 histograms, that means there's 4 times 4 times 8, which is 128 element feature vector. So this is not a vector in 3-dimensional space, it's a vector in 128-dimensional space. You could think of it that way. Where now we've got a 128 character long or number long descriptor for this particular key point. And that is, here are all of the orientation histograms of all the different bins that we've made. And all of these are gradient angles expressed with respect to the overall orientation of the key point. And then we're still not done. We end up with this feature vector. We still need to kind of groom the feature vector a little bit before it's ready to be compared to other feature vectors. We normalize the vector to account for illumination changes. To account for illumination changes. And discard outlier entries. And really, there's even more going on than that, but I think this is already complicated enough, and you don't really need to understand everything that's going on under the hood. Finally, almost done, SIFT feature matching. This is a short one. Okay. So essentially, you've got a 128 element long vector describing each feature in an image. Then what you simply do, if you want to see, like, oh, is this feature the same as this feature? You just do a nearest neighbor search. In 128 dimensional space. And it's simply just a minimum Euclidean distance. And there is, in the original paper, they recommend what's called best bin first, or BBF data structure to speed up search. Okay. And I'm also going to mention here, note, maybe not in, we'll do like purple. Here, hang on, bear with me, Peter. I'm almost done. Note, all of this is a massive simplification. SIFT is a lot more complicated than I'm letting on. I'm just kind of doing my best to make it make sense. Okay. Do not try to code up SIFT from scratch. Maybe you're feeling curious, you'd like to give it a try. You can. I just think the best you're possibly going to accomplish is to replicate the performance of inbuilt Python and MATLAB functions. And in general, even that won't work. Also, there are tons of helpful online resources, videos, etc. There's plenty of image processing people who can explain SIFT better than me. So if you'd like to learn more, you're welcome to look those up. Hopefully this at least makes sense from a distance. Okay, Peter, you've been patient. What can I do for you?
I was just going to note, when you said sample the 16 by 16 grid around key point, produce 4 by 4 orientation histograms, 8 bins each, 4 times 4 is 16, and you drew 16, but there were only 8. You wrote 8.
Help me out.
The third from bottom line in
Yep.
SIFT feature description, right at the end there.
Yep. Produce a 4 by 4 orientation histogram with 8 bins each. And I only drew...
You drew 16. You said there were 8, but 4 times 4 is 16. So I'm trying to figure out, is it like a 2 by 4 or is it 16 bins?
So there's 16 bins. And
Yes,
then, sorry. There are 16 histograms. Each has 8 bins.
Yes, but no, but where it says 4 by 4 orientation histograms.
Produce 16. That's what I mean. There are 16 histograms. Yeah. So you're taking the original 16 sample points. I'm not really doing the best job of drawing this here, but you're taking the original sample points. You're saying, okay, all of these sample points within a region, we're going to clump them together into a bin. So imagine that you have a 16 by 16 grid, and then you're saying, okay, all of the elements within this one. I'm trying not to overuse the word bin, because there's image binning and then there's histogram binning, and I feel like we're overstressing that one word. But we're saying, okay, for example, and this is not exactly to scale. Don't linger on these diagrams to get the exact numbers right. But the idea is that imagine that this is really supposed to be 16 by 16, and then this is really supposed to be 4 by 4. And we're saying, okay, these points are all going to collapse into one. And then really from this, we would take it even further and say, okay, this is theta, and then this is number. And we would go, okay, we got this many here, we've got none here, we've got this many here, we've got this many here. So then this gets collapsed into a bin where there are, sorry, into a histogram where there are 8 individual bins.
Oh, okay, I see. Sorry.
Yep. And then all of those, so now there's 8 bins in this, and there's 16 total of this, which gives us 128 unique numbers. So in the end, you're left with basically, if you line up all of your histograms, 128 individual, like a bar graph with 128 individual entries. That's the idea. And then that particular sequence of entries should be completely unique to that feature. So I think what might have thrown people off is I did not stick to these numbers in my sketch. Sorry about that. It's because if I tried to sketch that many, I'd be here all day. Yeah, it's a lot. I stared at this for several hours before it even started to make sense. So I might not be doing the world's best job of making it make sense to you all, but trying to get the rough idea across that your SIFT feature descriptor is basically a humongously long histogram with unique values in each of the bins. That's kind of what we're after here. And then what's filling the bins is individual gradient computations at subpixel points, which are near your original SIFT feature. And yeah, in my head that sounded really simple, but I realize that's a lot. So now, if this seems overwhelming, I would like to let you know that we are past the hardest point in this lecture. At least I think so. I think the rest of it's easier. Because when you actually go to code this up, it's going to be so easy. Right? Really, I just wanted to get this point across so that we understood a little bit of what's going on under the hood with SIFT. But next, I want to talk about practical application. Of SIFT. So it's time for some pseudocode. That was some feedback I got on homework 4, was that more pseudocode might have been nice. Ooh, you know what? Sorry. I'm going to change the order here. Moving this down. Practical application of SIFT is next. First, I want to talk about so what's going to end up happening is when you do SIFT features on image A, SIFT features on image B, and then find the correspondence between them, you're going to find that overwhelmingly the correspondence agrees, right? But it might not look quite like this. You might have a situation where, for whatever reason, it thinks that this point in this image is this point in this image. Because for whatever reason, the SIFT feature vectors just worked out that way. SIFT is not bulletproof, right? There will be mistaken, there will be false matches, right? So how do we handle false matches? How do we go, look, clearly all of these red points agree with each other. They're all like the same amount over and up. And this purple one can't get with the program, right? We clearly need to throw out that match and only keep the ones that agree with each other. So that's what I want to talk about next. So how do we only keep matches that agree with each other about the overall correspondence between points? What we do is something called random sample consensus. Then we will do the practical application of SIFT, which is just pseudocode. So random sample consensus, sometimes known as RANSAC, is a very popular method of outlier rejection. Used in several fields. So the idea here is, given a set of noisy data, and it doesn't need to be SIFT features, randomly select a subset of data. Fit that data to a model. And that model could be anything. Maybe you're trying to compute a line fit. Maybe you're trying to compute a homography. It could be anything you like. You fit the data to a model. Then you see how many other points, quote unquote, agree with that fit. And those would be inliers. And how many other points disagree with that fit? Those would be called outliers. So let's just do a quick and dirty example here. Let's say that we're trying to do a circle fit, and these are our points. You got one here, one here, one here, one here, one here, one here, and one here. Now, maybe this is a bad example for a circle fit. Let's give a few more easy ones, right? Okay. The point I'm trying to get across is that the circle, the real circle, is that. That's the real circle that's underneath all the data. Okay, but we don't know that, right? So in the absence of knowing that that's the real circle, we just have these data. What are we going to do? So one option is we say, okay, let's consider a few members of this data. Let's consider this point here, and this point here, and fit a shape to those. Stand by. That might look like this. You say, okay, if I fit a circle to these points, this one is kind of an inlier. Maybe this one, no, we don't like him, we don't like him, we don't like him, and we don't like him. Okay, so when I fit to these 3 points, I had 2 inliers and 4 outliers. Okay, save that, remember it, and then try again. Okay. Now let's try a different one, and then maybe this one is red. And now we say, okay, let's try fitting this one, and this one. Okay, and then you fit a circle to those. And when we fit a circle to those, this one's good, this one's good, this one's good, this one's good, outlier, outlier. This one had 4 inliers and 2 outliers. Okay, I think this might be right. And as a matter of fact, that's the best you're going to do. With this kind of distribution of points, you're never going to beat that number of inliers and outliers. So that's as good as that's going to get. So we have 4. Let me kind of clean this up. I was going to just erase this, but actually I think this might be a useful sketch. So we have 3 data points, or 3, sorry, I'm making this up as I go here. So this is a random sample of 3 points, fit a circle, and then when we do that, we find 4 inliers and 2 outliers. Hopefully that kind of makes sense. Okay, what we would do then is we would repeat this a bunch of times. So repeat many times, and just keep track. What inlier set, or sorry, what random sample gave me the most inliers? Right? And this many times is a tuning parameter. You get to decide how many we try. Because at some point you've got to give up. And what we do is we move forward with random sample that gave the most inliers. But there's one more step. Finally, we fit the best sample set and all the associated inliers to the model and return that solution. So our final answer for this particular ransack problem would be these 3 points gave us the best match overall. It gave us 4 inliers. Let's take those 3 points and the 4 inliers, that's 7 points, fit a circle to all of those. That's as good as it's ever going to get. We've just accepted that these points are outliers. They're duds. We found and rejected the outliers successfully. And we return the best possible circle that you can make, which satisfies the most points and kind of disappoints the fewest points. Points. So the question then is, what model are we fitting in homework 8, right? We're not doing a circle fit. What model are we fitting in homework 8? More on that later. I'd like to give you all a break at some point. Okay. So then finally, how do we actually use SIFT? Because we need to be able to detect features, describe features, match features, and get rid of the dud matches through ransack. So here's kind of what your pseudocode might look like on homework 8. So to be detect features in image 1, and then detect features in image 2. Then we would describe features, or I think the word is extract. And then extract features. Okay, so this is key point detection. And there's key point description. Then we perform feature matching, so match features, which, as the name implies, this is key point matching. Then we keep only match features. So key point matching would typically involve, ransack would happen here. Sorry, got ahead of myself. That is not where ransack happens. Key point matching happens here. Keep only matched features in image 1. So this is that Venn diagram part, right? We had a whole bunch of image 1 features, a whole bunch of image 2 features. We find the correspondence between them. Some of those correspondences are wrong, but if there's no correspondence found, we just throw it away. So we keep only the matched features in image 2. And so this is down selecting. Then we perform ransack on the matching points. Keep only inliers in image 1 points. And keep only the inliers in image 2 points. Okay. And so then this is basically further down selecting. Okay, so you can imagine there's like one of those Russian nesting dolls. So you've got all of the features that are in both images, and then you've got a smaller shape. Maybe it looks like this. Scoot over a little bit. And then a still smaller shape. Looks like this. Okay, so out here, we've got all detected features. Okay, and then you've got all matched features. And then finally, you have all inliers. So when we're done finding inliers, you should have something that looks like this, where you have a set of points in your first image, a set of points in your second image, and the correspondences between them all seem to agree. You don't have any duds where for whatever weird reason this crater registers as being this crater. You've gotten rid of those. It's nice and smooth. So you basically end up with pixel coordinates in the first image and corresponding pixel coordinates in the second image. And that is a prerequisite for actually solving the geometry problem at play, but we'll get to that after the break. This is going to be your pseudocode for basically the first half of homework 8. And what I like about homework 8 is if you do this in MATLAB, there is a kind of pre-worked example on the MathWorks website that shows how to do exactly this. And I mean, it's, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's roughly 10 lines in MATLAB to do all of this. And then in Python using OpenCV, it's the same game. There are very well-established ways of doing this. You don't need to reinvent the wheel. It sounds like a lot, but in roughly 10 lines in Python, you can go from, extract features in image 1, extract features in image 2, perform some correspondence, and then keep only inlier points. And then when you're done, you'll just have a whole set of inliers in image 1 and a whole set of inliers in image 2. And at that point, you're basically at the halfway point on homework 8, and that should take, I mean, certainly less than an hour. There's, tutorials on YouTube and all that. So that's what I like about homework 8. The other part, estimating how much the spacecraft moved, we're going to discuss that after the break. So take a minute for questions. Everybody's good? A lot to cover. I realize this is a dense topic. Let's take 5 minutes and cool it. It's 7:04. Let's take a break until 7:10. Okay, we're going to keep on moving. Welcome back, everybody. So a disclaimer. Technically, I don't think I'm allowed to force people to stay in class after 7:30. So you are welcome to leave if we hit 7:30 and you have somewhere you need to be. I'm going to keep yapping until we get through this material, and then I'll post the video and you can catch up with it later. So do not feel compelled to stick around if you have somewhere to go. But if you're interested, you're certainly welcome to stay here. So we've talked about how to get something that looks like this, which is image 1, image 2, features in image 1, features in image 2, find the correspondence between them, get rid of all the features that didn't match anything, and then get rid of all the outliers that matched in a way that didn't agree with the rest of the crowd, so to speak. Now we're here. But the question is, this photo, image 1, was taken with a camera on board a spacecraft, which was moving, right? And the way it looks like all the features move to the left, but probably what happened was the spacecraft is moving to the right, right? But how much? Like, you know, what is the direction in the camera frame? And then can we determine the change in orientation? What else can we determine? So that's what we're going to talk about next, and that is visual odometry. So odometry just means measuring distance. So think of an odometer, R, right? Distance since it left the factory. So visual odometry is estimating change in state using before and after images. Okay, visual odometry can be done with stereo image pairs or individual images. So if you have left eye, right eye, before image and after image, that's 4 total images. That is called binocular visual odometry. Or if you just have the one camera, before image, after image, there's 2 total. That is monocular visual odometry. There is a rich history of binocular visual odometry on Mars rovers. So we'll talk about that very briefly here, just because I think it's interesting, and then we'll move on to the actual math problem. So this was first employed on, so let's think about all the Mars rovers there have been. The first Mars rover was called Sojourner. It was in 1997. Then after that, in the early 2000s, there was the twin rovers Spirit and Opportunity. And Spirit and Opportunity. And this was flown as basically extra credit software. Like, okay, we know how to navigate a rover without visual odometry. We'll throw this on there for fun, but it's understood that, you know, if we get the chance to run this, it'll be something that we do for extra credit, right? Then it successfully determined the rover was stuck. literally spinning its wheels. And helped save the mission. So it's like the little nav algorithm that could actually help to save the mission. I think it was Opportunity. Oh, I might be getting them mixed up, but one of them was basically stuck in a patch of sand, and they would command it to drive a certain distance. And then for kicks, they fired on visual odometry, and visual odometry said, buddy, you told me to drive 50 meters and I drove maybe 2, right? Something is wrong. And that was how they were able to kind of diagnose the issue and get the vehicle unstuck. It would have actually dug itself in and gotten stuck there. So after that, visual odometry, or we're just going to say VO, was part of the main navigation concept of operations, or ConOps, on Curiosity. And now visual odometry is standard. It's on all the rovers. So Perseverance, the most recent rover, that used to be called Mars 2020. Perseverance does visual odometry in real time using a dedicated, it's called FPGA, Field Programmable Gate Array. It's a type of computer that is, if you know you're going to be doing the same type of calculation over and over and over again, you can basically hardwire your computer to do that. And it becomes extremely efficient at doing the same thing over and over again. So your standard computers are reprogrammable so that you can ask it to do a different thing. But if you know you have a board that all it's ever going to do is visual odometry, you can actually optimize for that and speed it up quite a bit. And so Perseverance doesn't even need to break stride. It can just keep on driving and do visual odometry in real time, rather than the old method, which was take a picture, drive a bit, stop, take another picture, sit there and process for a few minutes, get an answer, and then keep moving. Now it's like, nope, doesn't even need to slow down. It's pretty cool. In this class, we will focus on monocular visual odometry. And this would basically be an orbiting spacecraft looking at the ground. Okay. And monocular visual odometry can determine change in pose up to an unknown scaling. So basically it lacks depth perception, just like a Cyclops, right? So you cannot directly estimate position or velocity. You can only get the direction of motion. Or DOM. Okay, so let's start doing some math. So this is the monocular VO problem setup. Okay, so consider a spacecraft in orbit low over the lunar surface. Okay, so imagine that here's your terrain, and imagine that you've got your spacecraft, and I'm just drawing it as having a little camera here, and it's scooting along, and then this is at some time, we'll call this t k minus 1. And then at some future time, tk, here's the spacecraft again, it's going to keep right on going. Okay. And let's imagine that it's observing some point on the surface of the moon, like this. Okay. Where maybe this is some global reference frame over here. We know that this point is point I in the M frame. Actually, I'm going to do frames as a superscript for this problem. So point I, M. Okay. We know that the spacecraft is at position R, M, at time K. Ooh, that's a little bit busy here. Let me back off on that. So here's the vector. Here's the way we're going to write this. Spacecraft position in the moon frame at time K. And then similarly, there's going to be some spacecraft position in the moon frame at time K minus 1. Okay. We also know that we don't really measure the vector from the spacecraft to the point. We measure the unit vector from the spacecraft to the point. So we'll call this E hat. So we're back to hat being a unit vector. Ith point, moon frame at time K minus 1. And then here we've got E hat I M at time K. And already this is starting to get kind of busy. And then I guess one more step is we've got the change in position, which I'm going to write as delta R in the M frame at time K, where time K is basically current, and then K minus 1 is one time step ago. I'm also going to clean this up. Just give this one camera baffle. There we go. Okay, this is kind of busy. Let's simplify this a little bit. Okay, so here's our terrain. Here's our world frame. Here's some point P, I in the M frame. Okay, here is the camera. And the thing is, we're not actually measuring the position of the camera at either time. We're measuring how much it changed its position. We're measuring that delta R. So because of that, I'm just going to clean this up by removing those vectors. Say, okay, here is delta R in the moon frame at time K. Okay. And then imagine that you've got this unit vector and then some unknown distance. Here's another unit vector and then some unknown distance. Okay. And this is E, I at M in the K. This is going to be rho I. Okay. This is going to be rho I K minus 1. It's going to be E hat I M K minus 1. Okay. And just to be very clear, our notation is E I M hat K, where K is basically image or time number. I is the feature number. So those are our feature points. And then M is the moon-centered, moon-fixed frame. And then the hat is, this is a unit vector. Okay. Crucially here, note, go back to purple. For this lecture, we neglect the effect of the moon's rotation. Between images. I wanted to keep this derivation relatively short and sweet. Really, we would actually have additional steps to account for the fact that the moon is rotating under us as we go. Okay, so let's start our derivation by making some triangles. Where we'll say this, Rm at time k is what? It's going to be Pim at time k minus rho I at time k Eim at time k. So all we're doing is completing this triangle, right? Position, direction that we've measured, position of the point. That makes a triangle. Here's our triangle. And we can do this at two different times. We can also say it's further true that Rm k minus 1 is Pim k minus 1 minus rho I k minus 1 Eim k minus 1. Okay, so point P, if we haven't made this clear already, is some landmark that we can ID correlate between images. It is a SIFT feature. You might be saying, well, Paul, you've taught me how to find point correspondence between digital images, not how to go look up the 3D location of a SIFT feature on the surface of the moon. Aha, here's the beauty of it. It's the same point. It didn't move between image 1 and image 2. So in the equations to follow, because Pimk and Pimk minus 1 is the same, we can actually subtract it out. We never need to look up the real 3D location of any of our SIFT features. We just know that feature looks like it moved this much. I know it didn't really. Okay, here's how much I moved. That's basically the idea. So if it is the same feature, if it is truly same feature, it does not move. In the MCMF frame. And that's really the beauty of this. So we can say position in the moon frame at time k minus position in the moon frame at time k minus 1 is equal to point I in the moon frame at time k minus point I in the moon frame at time k minus 1 plus rho I k minus 1 Eim k minus 1 minus rho I k Eim k. The beauty of this is that this cancels out, which is nice. And also, we're going to define that the change in position is defined as delta R at time k. Okay, so we never need to know a feature point's true location. It cancels out.
Professor,
Yes.
this might be a dumb question, but it's moon-centered, moon-fixed reference frame, right? So what if those times are long enough to where, like, the moon, it moves?
The moon will rotate, right? But in the moon-centered,
Yeah.
moon-fixed frame, it won't. Right? The same way that the
Sure.
location of Troy, New York in the ECEF frame is constant. But the location of Troy, New York in the Earth-centered inertial frame is not, because the Earth is spinning. But we're doing our work in the moon-centered, moon-fixed frame.
Okay, thank you. My
Does
bad.
that
I think.
help?
Yeah, I
feel like
understand.
that didn't quite connect it. Are we still good?
No, it did. I was just being silly. I understand
Nope,
now. Thank you.
a-okay, not to worry about it. Now you might be saying, but the spacecraft is in an inertial orbit. It's not like flying over the ground, and the moon is rotating. And you're right. So there is the effect of the moon rotation, which we are just ignoring because we're saying these photos are taken seconds apart. But you're right, that will introduce some error. And what we're doing for homework 8 is kind of a simplified version of this math problem. Really, there's more that you can go and read about if you want to take into account the moon's rotation. But for now, we're going to ignore that. So we still have unknown ranges to deal with. Also, we have our measurements in the camera frame. So first I'll mention, we take measurements not in the moon-centered, moon-fixed frame. We take them in the camera frame. And also, as drawn, I don't know if I showed this, the camera is rotating, right? It's actually slewing. So the camera is translating and rotating between images. We don't necessarily know what that is. We're going to want to account for that as well. Okay, so let's write our equation like this. Delta R M at time k is rho I at time k minus 1, and then the direction cosine matrix from the camera frame at time k minus 1 to the moon-centered, moon-fixed frame. And then we have EI in the camera frame at k minus 1 at time k minus 1 minus rho I k t ck to m EI ck at time k. Okay, this is a little bit better because we get unit vectors in the camera frame. We talked about how to find unit vectors in the camera frame, right? To go from our SIFT features to our unit vectors in the camera frame, I believe that was all the way back in lecture 16. Don't quote me on that. You'll have to go back through the lecture notes. But we can do this, right? This is findable. These ranges are not, right? So we're going to have to do something about them. Let's see. So for convenience, let's choose to work in the camera frame at the time image K was taken. Okay, so here's what we're going to say. The direction cosine matrix from the moon to camera K, and then we've got delta R in the moon frame at time tk. We're just taking delta R and expressing it in the camera frame instead of the moon frame. Well, this is what? This is rho I k minus 1 t m ck t ck minus 1 to m e I ck minus 1 at time k minus 1 minus rho I k t m ck t ck to m e I ck at time k, where all we're doing is this now cancels out to be the identity. These two matrices, so we're going from camera at time k minus 1 to the moon frame, and then the moon frame to camera at time k. This is just t ck minus 1 to ck, which is the rotation, right? So we have the rotation of the camera between the two times is now expressed here explicitly. Finally, this, we're just going to call this delta R in the camera K frame at time K. Yes, Peter.
Just making sure that the CK minus 1 and the E in the EI, that's just notational to say that it's in that frame.
Yes. Yep.
All right.
So we've got the, in this point right here, that is the ith point in the CK minus 1 frame. And we don't actually know what that frame is. It's just expressed in its own local frame. And here we have the relationship between the two frames, which, not to spoil it for you, is something that we want to solve for. So actually, I might take a moment and say, we want to solve for this. And also this. We want both of those. Okay, so let's take a second and rearrange. Okay, so we're going to just going to move some things around. Rho I k minus 1, T ck minus 1 to ck, and then we have E I ck minus 1, k minus 1, minus, and then we have delta R ck at time k. This equals rho I k E I ck. Okay, all I did is move some things around. Okay, now let's use the old cross product trick. From the direct linear transform derivation. So all the way back in lecture, gosh, 13, 14? Yep, all the way back here. Boy, my handwriting did get worse. Sorry. We're using this trick where we're getting rid of the UI. Basically, we end up with a direction crossed with a direction, and that cancels out. Right. We're going to bring that trick back again, all the way here in lecture 25. Okay, so what we're going to do is we're going to say, okay, this is now rho I k minus 1, and then we introduce this new matrix, delta R ck cross. So it's the cross product matrix made out of this delta R ck. And then we have T ck minus 1 ck, E I ck minus 1, k minus 1, minus, what we end up with here is delta R ck cross with delta R ck, which is just a vector crossed with itself. So we've successfully gotten this to cancel out. And this is equal to rho I k delta R ck cross E I ck at time k. Okay? And now finally, let's see here. Okay, we're going to left multiply by this EICK, if that makes sense. So the three vectors in question, right? We've got the amount that the spacecraft moved, we've got the vector from the spacecraft at one time to a point, and a vector of the spacecraft at a different time to the same point. That's a triangle, right? We've got, this is kind of a little bit busy here, but we've got this vector, and this vector form a triangle. So we can actually leverage that triangle here to make our math a little bit simpler. The three vectors in question are coplanar. So, because they form a triangle, okay, here we go. And I promise this is getting kind of busy, but we're actually almost done, at least with this part of the derivation. We have rho I k minus 1 E I ck k transpose delta R ck crossed T ck minus 1 ck E I ck minus 1 k minus 1. So we're left multiplying by the EI vector transposed at time k. And when you do that, it's equal to what? Well, it's equal to rho I K, and I just found a mistake in my notes here, stand by. Wow, this is all so simple and clear. How could I have made a blunder in my notes? Apologies. And then this is what? This is EICK, K, transpose, delta R, CK crossed, and then EICK. Okay, so now you end up with R crossed with this vector, but then you take the transpose of that with this vector. Well, now by definition, that's going to be 0. So we've successfully zeroed out the right side of this equation. And what we end up with is this. Finally, we are left with a null space problem. We can drop our range. Right? We're ending up with basically a matrix of the form AX equals 0. And the thing is that it's just as easily true if 2AX equals 0 or if 3AX equals 0, right? You can just kind of drop your scalar term because you're going to end up with this unknown range. By the way, this unknown range is the same unknown range that we discussed kind of qualitatively earlier. Here it is actually showing up in the math. Because of that, we can just say, okay, divide both sides of the equation by rho I k minus 1. And we end up with this. EICK at time k transpose, and then we end up with delta R CK cross product matrix T CK minus 1 CK, and then EICK minus 1 K minus 1 is equal to 0. Or we can take this middle part if we want to. It is going to be a cross product matrix multiplied by a direction cosine matrix, which is still going to be a 3 by 3 matrix, and we're just going to call it E. Okay? And I'll say all our interesting state info lives in the E matrix. And our measurements are on the sides. Okay, so we're going to end up with something that we can get directly from our measurements times E times something else that we can get directly from our measurements equals 0. Solve for E. Right, so there's that whole math problem. How do we solve for E? And that is called the 8-point algorithm. And then we can actually extract delta R and T from E, which is its own thing. And I'm looking at my notes and I'm realizing that we probably have 20 minutes worth of stuff left. And that's going to put us over our hard stop. So I think what I might do, I think perhaps I was too ambitious when I put all of these lecture notes into a single lecture. I think if I had this class to do over again, I would try to do OpNav in 1.5 lectures and then visual odometry in 1.5 lectures. That would keep the total count the same. But anyway, live and learn. I think I'm going to stop here and let's pick up next time. So we'll just say to be continued. Actually, I like my to be continued from, where was it? Yeah, let's borrow this one. There we go. So we'll be to be continued, and we'll come back next time and we'll finish up how to solve homework 8. And in the meantime, I'll say thanks everybody for your patience through what was perhaps a too dense lecture. I'll try to thin this out for the next time I teach the class. But let's stop here. Anybody have any questions on the stuff we've covered so far? I recognize we didn't finish the derivation. There's still more to do, but hopefully we have at least a decent grasp on what we've accomplished and what still needs to be done. Cool. Okay. I'm going to stop here and then we'll end the recording, but I can stick around at least for 15 minutes if people have questions on the homework.